Hi everyone, welcome to the series Beginner's Guide to Bare Metal C. This is a learning series where I will share my experience, things I learned and the problems I faced along the way. So it won't be a perfect expert tutorial, but a basic one that will grow as I learn more stuff. Today we are going to go through the why, where and how of Bare Metal C first. Bare Metal C is used because it gives more control over the hardware for more advanced and custom firmware development, which is not supported by pre-existing libraries. It is mainly used in industry custom firmware development or custom hardware programming where you need full control over what the hardware is doing and when. There are IDEs such as STM32Cube IDE for writing, compiling and uploading code to the microcontroller. The code is written in C, compiled to binary files which is then uploaded to the memory of the microcontroller. Now let's take a look at what bare metal C actually means. Bare metal C refers to directly writing firmware to the hardware of the controller we are using with little or no abstraction layers by using direct register addressing. Basically what you do here is control the registers directly and by using them perform specific actions on the hardware of the microcontroller. No library is doing things behind the scenes. Every action is something you explicitly wrote. Registers are basically a set of flip-flops, specifically D flip-flops. They store data and that stored data is wired into different hardware using different combinations. So when you store a bit in the register location, it gets interpreted by that specific register's hardware as a specific command. For example, let's take a 4-bit register which is basically 4 D flip-flops connected in parallel, and you can specifically load a value into any one of them. Each of the register bits connected to the base of a transistor which powers an LED. So when all values are 0, no LED will be on, and when all are 1, all will be on. In this way, we can control which LED turns on by storing the specific required values in those specific register location. This is essentially what bare metal programming is. You are directly talking to the hardware through these registers. These register actions are done by bit shifting and basic logic operations. For example, we use OR to set a bit high, AND to clear bits, and XOR to toggle bits. So for example, 1 left shift by 3 means you are basically shifting 1 by 3 location into left side, which will create a value with the 4th bit set high, which is basically binary 1000. Using this, we can perform normal logic operations like setting a specific bit in a register without affecting the other bits, which is important because registers often control multiple things at once. The microcontroller I am using is basic and cheap clone board of the STM32. It's a STM32F103 blue fill board. It's perfect for starting because first of all it's cheap. You don't have to worry about making mistakes and damaging the board, and it has enough specs to handle any beginner programs. The tool I use to program this board is STM32Cube IDE. Although I had a problem with my microcontroller not connecting to it and being unable to directly upload it to it, it's enough to write the program and build the binary file. If you get the binary file, you can use another simple software called STM32Cube program to upload that file to the microcontroller from there. It's a little bit of extra work, but it works without problems. If I do find out why my IDE is not able to direct the board, I will post video about it, and if you know why, please leave your advice in the comments for me and others who are facing the same problem. Now let's look into the registers of an actual microcontroller. You can use the official STM reference manual for the board you are using, although it's usually 1000 plus pages and can be genuinely confusing if you're a beginner, which was my experience. It does include deep dives into all the hardware, which is good for professionals, but in my opinion, if you try going through it as a beginner, it might just confuse you more. If you can genuinely navigate it, then great, you already have one big problem solved. But if you can't, there is another simpler way. There's a website called STM32 Peripheral Coverage where you can click on your specific STM board and it will give you all the register details for your board without the extra hardware details. I will give the website link in the description. The important thing about these registers is that you don't have to remember all of them. It's really hard because there are so many of them. Even though you don't use all of them most of the time, the names can be confusing and you forget things. But it doesn't matter. You can have the register guide right next to you while writing the program. You just need to have the basic intuition into what does what, like GPIO controls CPU, TIM controls timers, RCC controls clocks, I2C controls I2C communication, etc. This basic knowledge will help you use the guide effectively. And if you forget, there's always the internet and you can check the specific register name and jump right back into coding. Now let's write a simple program to see how it all comes together. The first line is header file. It basically contains the register mapping. It maps the human readable names to the actual memory addresses of the registers in the microcontroller. You can write the program without it, but writing the full register address every time would be hard. So commonly this header file is used. Also an important thing, it will be different for different STM boards. Mine is STM32F103 and there won't be a huge difference, but it varies across boards because the hardware varies. So rather than writing pure register address like 0x7C000U, which is a lot of zeros to remember, we go for the simpler way, just writing the human readable names like TIM, RCC, I2C1, etc. The second line is the start of the program. The main function, it's where all your C programming will go, where the configuration will be done and where the program loop runs. In Arduino there are setups and loops functions, but this is the bare version of that. Basically inside this you write the setup first, which execute once when the program first runs. Then you write the while loop that will always run like the loop function in Arduino. We will write an LED blink code. To write that, first we need to check which pin the built-in LED is connected. Since I am using the built-in LED, if you are using an external LED, you need to check which pin we will be connecting it to. Now once you have the pin name, you need to check which hardware block it belongs to. Basically in STM boards, the pins are grouped into separate blocks like A, B, C and so on, and each block will have certain number of pins in it. For my board, the built-in LED is connected to PC13 and as the name suggests, that pin belongs to the C block. So now I need to enable the clock for that block. Normally the clocks are disabled for all peripherals blocks by default. This is done to save power. For a pin to work, you just first need to give that specific block its clock. This is done by using the APB2ENR register in the RCC group. As mentioned earlier, RCC is the clock control register, and inside it the APB2ENR controls the clock for the C block of GPIO pins and some other peripherals. Once it's enabled, the C block of the GPIO is active and ready to use. Now we need to configure the pin as output. This is done by using the CRL and CRH registers in the GPIOX collection. CRL controls the pins 0 to 7 and CRH controls pins 8 to 15. For pin 13, I need to use the CRH registers inside the GPIO C block. There are two things to configure here: the mode, which tells if the pin is output or input, and the configuration, like for inputs whether the pin is floating or pull up or pull down, and for outputs whether the pin is push pull or open drain. I will set the mode as binary 10 or decimal 2, which is output at 2 MHz frequency. No need to worry about the frequency for general LED blink, you can just set it to the lowest one. And I will set the CNF or configuration as push pull because I want the microcontroller to actively drive the LED on or off. And lastly, let's make sure the LED is off at start. This is done by using the ODR, which controls the port output. Since I need the LED to be off, I will set the bit 13 of the ODR low, which controls the output of pin 13. So now the LED will be off at the start. This is not critical, but if you want to start from a known state, you should do that. Now the static configuration part is done. Let's look into the loop of the program. This is the part which will run continuously after the configuration is done. Inside it we will write the actual blink code by using the same ODR register, but now we will make the bit 13 of it to actually toggle every time this loop runs by using the basic XOR operation. So now every time this code runs, bit 13 will flip and cause the output data to flip as well. For example, if it was 0 in the first run, it will become 1 in the next, and so on. It will keep changing and consequently make the LED toggle too. And lastly, we will add a small delay by using the simple for loop to reduce the speed of the loop iteration, so we can actually observe the LED blink without this delay. The LED would be toggled so fast we wouldn't be able to see it. Then you select the build project option in the IDE to get the binary file. Also, you need to enable the settings in the IDE configuration to actually generate the binary file, otherwise it will not produce it one. I highly suggest going through an IDE tutorial to get a better understanding of it. So once you get the binary file, you go to the Q programmer, open the upload tab, select the file and upload the code. This is only needed if your IDE is unable to detect the board. If your IDE can successfully detect the board, you can upload the code directly from there without needing the binary file separately. But if not, this is the easiest way. And there we go. Now we see the LED blink in real time, and that's how we write a bare metal C program. There's a lot to learn in this field. This is basically a very basic intro, but a helpful one to get started. Thank you for watching. If you like the video, hit that like and subscribe button and leave a comment. See you in the next video. Have a good day.